Hello, everyone, and welcome to another Safer Sim webinar. Today, we have a colleague from the University of Puerto Rico at Mayaguez. During the presentation, if you have any questions, please feel free to unmute yourself and ask. Otherwise, you can also type them in the chat, and I will read them out at the end of the presentation. And with that, I'm going to hand the floor to you, Alberto.
Thank you very much, Don, and I want to also thank Safer Sim for this opportunity to present this research as part of the Safer Sim program here in Puerto Rico. I am a professor of civil engineer and also co-director of the LTAP program here in Puerto Rico, and this has been a pleasure for me working on this project related to modern roundabouts using virtual reality. So. I want to introduce first the research team that participated in this project. Included Dr. Didier Valdez and also Dr. Yvette Cruzado. Both of them are also professors in the transportation area here in University of Puerto Rico, Mayaguez. Dr. Valdez is also the associate director of the Safer Sim group here in the University of Puerto Rico. And we had three research students with us. Natasha Cardona, she's a master's student, civil engineering. And we have Dr. Andres Chamorro. He was a student at the computer science and engineer. He already graduated from his PhD. And we have also Jan Badillo, who is a bachelor student from the software engineer. And we also had a fourth student, Janilet Rodriguez. She assisted us during the data collection process, and she already graduated. She also is from the Bachelor of Software Engineering. So the agenda for today includes four major topics. Basically, I want to talk about what is the research problem and the objectives we have with this study. I'm going to talk a little bit about the development of the virtual reality scenario so you can understand the different factors we selected in the design of the roundabout and the experimental factors we decided to include in those as well. And then I'm going to present some of the results we obtained with the limitations and also some of the issues we found in the process of conducting the experiment, with some conclusions and recommendations on the end. So the basic for this project was roundabouts. Obviously, the design and construction of roundabouts in the United States has increased significantly during the last 30 years. Obviously, they have been promoted by Federal Highway Administration, different entities due to obviously their innovative design. And it's not like United States didn't have any experience with circular intersection. Obviously, there are different, type of intersection, but circular intersections in United States since the beginning of the 20th century, they were present in many cities. They had, they were a little bit deemed inefficient and unsafe. And it gave them a little bit of bad rap in some places. They don't like them, circular intersection. But the one we are talking about is modern roundabouts. So usually they have been developed mostly in Europe in the 60s with two major modifications that we have obviously on today's design. And that is the yield to circulating traffic in the roundabout and the geometric design of the entry and exit legs focus on reducing or slowing down vehicles. So those two modifications provided good benefits in terms of safety. And this increase in numbers has been documented by NCHRP. There is a website. You see the QR code that the people that work on that project, NCHRP 572, develop a website that it has an inventory of locations of roundabouts in the United States, and those are the maps they have developed through the years. So you can see that right now there are about 10,000 registered locations in that database. And obviously the benefits on this modified design for the roundabouts allows a general safety improvement in the number of crashes, number of fatalities for all users, not only pedestrians, and particularly due to the two aspects of the design. Obviously, the reduction in vehicle speeds is a major factor on the severity of crashes, and also the reduction in the number of conflict or potential conflicts on the intersection. When you compare those to a conventional four-leg intersection with the roundabout, then you have a number of, reduced number of crossing conflicts, which typically are severe due to the speed of the vehicles and obviously the angle. And also for pedestrians, you see that there is a potential reduction from 24 to 8 crossing conflict with pedestrians, which obviously helps in the safety level of this intersection. Nonetheless, still there are some issues or concerns pedestrians in terms of the geometry of the entry and the exit legs, the location of the crosswalk with relation to the roundabout. And also another issue is related to pedestrians that don't want to go to the crosswalk because they want to shorten their distance and use the middle of the roundabout to cross. In some location, you put a nice, beautiful statue or something in the middle of the roundabout, and people want to take a picture, so they cross through the middle as well. So that creates obviously a safety issue in the design and operation of roundabouts. But in technical, operational terms, there are two issues that we have to look in the design of roundabouts related to the entry and related to the exit. This study looked to measure how pedestrians made the decision to cross at the roundabout and how the geometry of the roundabout influenced that decision. And this topic is highly relevant as these roundabouts continue to be used and implemented more and more by the states. On the entry level, the issue is, well, while the drivers are slowing down, obviously, to enter into the roundabout, that's a positive aspect for the pedestrian crossing because drivers are slowing down. But we have to remember that the driver entering the roundabout will be focused on traffic in the circulatory roadways. So the attention of drivers might be looking toward their left to see if they have a gap that they can cross and don't have to stop or even yield to other vehicles. And if you have a problem with pedestrians coming from your right, you are not looking to them. So you might have a pedestrian coming from your right and you are looking at your left and you don't see them. That's an issue that has been identified in the literature. But on the other side, on the exit of the roundabout, the literature has shown that the exit movements are more critical for pedestrians because still pedestrians will still need to analyze traffic for gaps and analyze the speed, the time, the distance from the vehicle from the crosswalk in order to safely cross through the crosswalk at the roundabout. So especially senior pedestrians, persons with disabilities will have more issues or more challenges to do the crossing of the roundabout at those locations. So we wanted to analyze how the exit situation. We decided at the beginning, okay, let's focus on the exit and exit of the vehicles and the crosswalk at those locations. This is the fourth study we have done here in Mayaguez using virtual reality simulation. So the development of the technology has been, a huge advantage for doing this type of research. Obviously, you have to understand the limitations that the technology also allows to study in a controlled environment. And obviously, we don't want to forget that this is a simulation. So how do you are able to mimic or establish kind of real life conditions? Obviously, that's the main challenge as a researcher. But many people, especially colleagues in University of Iowa, Dr. Kearney, Dr. Plummer, they have used virtual reality and they have shown that the technology can be used to study human decisions. And actually, our first study, we had so many help from Dr. Kearney, Dr. Plummer that they allow us to let's say grow in this type of study and use the technology. But other researchers as well have demonstrated the capability of virtual reality, understanding their limitations and their capabilities to do this type of project. And I wanted to quickly talk about those three projects because it is useful to compare our results on this project. The first one, we analyzed the gap acceptance and walking speed of people on a mid-block location on 1 lane and 2 lane. And we measured walking speeds, their gap acceptance, and we found out a range, for example, from 4.1 to 4.8 feet per second. And there were several factors: the age, gender, the number of lanes, 1 versus 2, and the traffic with constant gap. In our first experiment, we analyzed 2 situations, random gaps and constant gaps. We didn't do it because of thinking of autonomous vehicles, but in reality, it is a nice feature to have a traffic on constant gaps, thinking as a platoon of autonomous vehicles. So we analyzed short gaps, constant gaps, and larger constant gaps to see what was the effect. And obviously, the walking speed, people realized those gaps and adjusted their gap acceptance on those locations and their speeds. And the vehicle gaps were about 4.5 seconds on average. Also, we analyzed the probability of being hit, and those increased with age, with the vehicle speed, higher vehicle speed, and shorter vehicle gap. So the probability was obvious. Those 3 factors are very obvious from when you see them and analyze them. And obviously, you want to go into more details, you can go to the SaferSync website. We publish a paper in the Accident Analysis Prevention about these results of this project. The second one, we upgraded the problem, and we decided, okay, we have the mid-block location, and we have the straight segment. What about if I have a person on a connected environment and they have a tablet-like instrument that tells them information about when it's safe or not to cross? So we added a RIAS, a road information assistance system with two levels. One just showing, you see in the screen, symbols, pedestrian symbols of walk and stop. And we did it again on 1 lane, 2 lane. I'm showing you the 2 lane setting. And people use this on a simulation. They have like a tablet, they see it on the screen, and those symbols change from walking to stop depending on the distance of the vehicle. We calibrated that device based on the actual walking speed of that person. So that's focusing on the enough time for the person to cross on that speed. And on the complex RIAS, we added more information. We added the speed of the vehicle per lane, the time it takes the vehicle to reach the crosswalk, and also we added the distance. At the beginning, we called them the complex because we say, okay, you have more information to understand, to analyze, to decide whether to cross. So we wanted to check if this, instead of helping, will become a distraction to the person trying to understand, okay, what this device is telling me, or let's say, no, I'm not going to use it and cross. Interestingly, walking speeds were very similar to the last experiments, and also age and gender were significant, but also the RIAS. If it's a simple versus the complex, we had a third setting that is no use of RIAS, so people cross without the device. And the gaps were larger. Now we are seeing people are taking larger gaps to cross, probably because of the distraction of the device, or because on the previous example they were too aggressive. So it is nice to understand what's going on, but they took longer gaps to cross. And interestingly for me, because the simple RIAS, the one with the symbols, was the worst performance. So people got hit by vehicles more with the simple, and we had a survey at the end, and people prefer the complex, the one with more information. And the information they thought it was more useful for them was the time for the vehicle to reach the crosswalk. Everybody said that amount of information was good for them to allow them to decide to cross or not. So it was very interesting. The third one, we moved to intersection. That was this is project we presented 1 month ago, and this was related to right turning lanes. We decided to design a channelized right turn lane, and we want to check if the length of the lane, the radius, the trajectory of the vehicles entering that lane. As you can see, there were two trajectories, one yellow and the blue one, to see if those factors affected the decision or the speed. And as you can see, the speed basically was similar to the previous 4.2 feet per second, and there was a slight effect on the radius of the turning lane. We used 60 feet and 30 feet to make those adjustments. And also the gap was very similar to the previous example, 6.8 seconds. So compared to the straight segment, those locations were more complex for the pedestrians. And then we move up to roundabouts. Obviously, as you can see, as we have progressed in the study, we decided to make this thing more complex. And obviously, that's I guess that's the vision of a researcher. We want obviously to increase complexity, and with that, we also run into a lot of issues. We wanted to see if the size of the roundabout, the trajectories, the crossing direction had any impact, and we did the same analysis. We measure speeds and the gaps, and we used the HTC Vive for the equipment. This is the same one we use for the other three projects. Let me move on so we can go to details. The roundabout, we designed it using the guidance from the SRHRP guidebook. And for the traffic controls, we follow MUTCD guidance. And we have two sizes of roundabout, small and large. And these are the details about those dimensions. We use NCHRP. They have different categories: mini roundabout, single lane roundabout, to multi-lane roundabouts. Those two roundabouts, 87 feet, can be considered a very, very large mini roundabout or a very, very small a single lane roundabout. So we wanted to be on the in that limit, and then we went to 120, which is a big single lane roundabout, to see if those extremes had any impact. The other elements were based on the design guidance, so we follow those as much as possible within the design. We use AutoCAD, and then those were transferred, and we use Unity, the Unity engine, to code and program the scenarios. As you can see, those were the design features of the roundabouts. So the small roundabout and the large roundabout become a configuration for the experiment, and we have two additional factors. The direction the pedestrian was walking, if it's either to the median or going to the sidewalk, and also a single and a dual trajectory, and I will show you those very quickly. We had a sample of 18 subjects at the end, nice subject for configuration, about 288 crossing observations, and traffic flow through the roundabouts. We use random gaps from 2 to 8 seconds. Traffic speed, we decided to have a very low speed flow, 15 miles per hour. It was constant. We didn't want to add it as a factor in the experiment. And we had 3 vehicle generation points with 2 potential conflicts with the pedestrian. And I'm going to show you, we had this first one. I didn't mark it, but let me see if I can put the pointer here. Okay, I hope you can see my red pointer. The crossing was the south leg. So we had the pedestrian going in this crossing, and we had one trajectory that entered the roundabout and exit toward the north. That didn't have any issue with the pedestrian. The second one was coming from the north, going through the south, and a third one going from the west, going south, making a right turn. So there were two potential vehicles or two trajectories, potential trajectories in conflict with a crossing pedestrian. And here's a quick video that you can see, but I need to change it, the pointer. Okay, so you can have a perspective of what the pedestrian was watching in the simulation. Remember that pedestrian is on the south leg looking, in this case, toward the north side, and now he's looking at the west side. And then he has to check traffic. All the vehicles coming from the north and on the west side are exiting toward the south leg. So all vehicles are exiting. Remember that the first one is going north, so those are not coming through the crosswalk. So that was the first factors of single. We call it the single trajectory. And then we added a second, we call it the dual trajectory. We have the same blue vehicle that didn't have any impact to the pedestrian, but it was added so people can see traffic going through the runabout. So now you have the vehicle on the red having two choices, either to exit or keeping the circulatory roadway. So we added some complexity to the decision. Now pedestrian has to understand if that vehicle that is coming from the north is exiting or keeping, the circulatory roadway, and the same we apply it to the west, from the west. So obviously it was more complex to order to program the gaps. So we can have obviously measure the gap that the pedestrians was selecting to cross. But as you can see on the video, now we have vehicles coming toward the crosswalk or keeping the circulatory motion on the roundabout. So now pedestrian has to understand what's going on and make a decision to cross or not. Okay. So let's go into the results. When we go to vehicle gaps, we analyze the three factors: roundabout size, crossing direction. Those two didn't have any impact on speed. As you can see, statistically, those were similar. The distributions were similar, but the vehicle trajectory, now having that issue of trying to understand if the vehicle is coming my way or not, that level of complexity increased the gaps that people accepted to cross. So it added basically half a second in the average value of those pedestrians working on those situations. In terms of average walking speeds, the direction of the crossing didn't have any major impact. Our initial hypothesis was that because the direction people had to look, turning their heads and so on, might have some influence on their behavior, and we didn't find out that that was the truth in that case. The size of the runabout didn't have any, well, they have some effects, sorry. They are different. The issue is that they were not normally distributed. So that was a surprise. In other projects, we have found out some normality. In this case, there was no normality, but they were different. So there was some effects in terms of the runabout size. People tend to walk faster on the small runabout, probably due to the size. They felt the vehicles were more closer to them. The large circulatory roadway obviously gave them more, let's say, perception of safety, because remember, the speed was the same. So it's not like in reality you may have a large runabout, people will go faster, but that was not the case in this experiment. We decided to keep the vehicles the same. So it's a factor of the size and the distance to the crosswalk. In terms of the vehicle path and the size, when we combine those, we confirm that the size does not have any major impact on speeds, on walk speeds, but the trajectory did it. You see that the difference on the left and the right side values, the difference are related to the paths. If it was the dual or the single path, and that was the difference, basically. So in conclusion, to give some time for questions, we find out that the size of the runabout influenced the walking speeds. Our assumption is that people felt safer conditions on the large roundabout, and therefore they decided to use slower speeds. And again, the issue is probably the large circulatory roadway. They allowed them to see the vehicle with more time to decide whether to cross or not. Those walking speeds were comparable to the other projects. There were no major difference. Older subjects had lower walking speed as expected, probably half a feet per second less than younger people. The gaps accepted to cross were not influenced by roundabout size or the walking direction, but they were affected by the trajectory. Like I said, we think it presented more difficulty to pedestrians, so they require a larger gap to cross. There were 9 collisions with vehicles. Older subject had a worse performance. It was about 93% success rate. I didn't add those statistics here in the presentation, but yeah, we found out that older people had worse performance. Because we had a small sample, we didn't want to get into conclusions because obviously we need more statistical significance to make those conclusions. And future studies, we can add additional factors to the experiment, such as the location of the crosswalk. I didn't talk about it. The location of the crosswalk was based on the middle value, the range that the NCHRP suggests in the location of crosswalk related with the circulatory roadway. So we can either move it forward or move it closer to the runabout. We can have higher vehicle speeds or higher than 15 miles per hour. And we can also add the 2-lane runabouts. That will make a more complex, obviously, analysis and coding of the vehicles. So with that, I want to thank the Safer Sim and thanks for all those who connected to the call. So we still have a couple of minutes if somebody has a question.
Thank you very much. Are there any questions?
I want to recognize that the 2 other authors are present. So if I don't have the answer, they might have it.
Sure. That's true.
Yeah, I have a question, Bruce Robinson from New Zealand. I wanted to know, in your simulation, you show zebra crossings, which implies priority for pedestrians, but was that in fact the case? Or were they accepting gaps? Because in New Zealand, and I think USA, a zebra marking gives the pedestrian priority. So was that just an artifact of your simulation?
That's a good question, and I forgot to mention that factor. In our simulation, we do not program the vehicle to react to the pedestrian. So basically, it's like the vehicle is in a uniform motion, and there is no slowing down or accelerating. It goes at constant speed, and there is no confirmation of a driver giving you way to cross. So it's up to the pedestrian to decide whether to cross or not. And
okay, so true gap acceptance. And my other question was, when you had on the exit a vehicle choosing to either exit or continue to circulate, were the indicators on for the vehicles? Was the subject pedestrian reacting to indicators on the vehicle, or were they just trying to guess?
No, there was no way to know, because we switch colors, we switch the 2 directions. So it was up to the pedestrian to say, okay, there might be a learning curve as well, because obviously the path is programmed in the simulation, but there's no other clear indication to tell the pedestrian this is a vehicle that is going to go south or keep on the circulatory, because it was randomized in the experiment.
So no turn signals, Alberto?
No,
right?
no turn signal, anything like that. Yes.
Okay, Thank you.
I guess colloquially I can say we follow Puerto Rico standards.
Thank you very much. Any other questions? Okay, I don't see anyone unmuting and I don't see any typing. Alberto, thank you very much for a very interesting presentation and for connecting it back to the other projects, because I see them as all a series of projects where the results are interconnected, or at least interesting together. So thank you.
That's a full story of the whole, progress in safer scene when you
Yes.
try to increase the level of complexity in the next research and so on.
Absolutely. And so thank you very much. I am going to stop the recording now.